Hello again, and welcome to lesson number 3 on the topic of implicit differentiation. In this lesson, we will make use of the tricks we've learned in lesson 1 and lesson 2 of this section, together with some of the concepts we learned in 5.1 and 5.2 to solve questions such as what you see here. All right? In this question, we are asked to consider the equation x cubed plus y squared minus 3x equals 0. You can think of this as a relation or as a function. The first pass is to find dy by dx, that is to differentiate. And then we are told point P and Q lie on the graph of this equation, or the graph of the function, and that the tangent through the point P is parallel to the x-axis, while the tangent through point Q is parallel to the y-axis. We are then asked to find the possible coordinates of the points P and Q. Now, before we begin, we're going to look at some facts related to what we've learned on differentiation. We'll just run through those few facts, and then we will solve this problem. Okay, let's see how we go about it. So here are some facts that we need to know before we solve this question. The first one is simply about parallel lines that are parallel to the x-axis versus lines that are parallel to the y-axis. We know that if any line is parallel to the x-axis, then the gradient of that line is always going to be 0. Okay, so any line, if a line L is parallel, so that symbol there is for parallel, if a line L is parallel to the x-axis like that, then we know that its gradient is always going to be 0. That's important for the discussion we have under differentiation. And if a line is parallel to the y-axis, if we draw a line that is parallel to the y-axis, then the gradient of such a line will always be infinite. Okay, so this is something that we already know, I think basically from when we started learning about differentiation. Okay, so that's a set of facts number 1. Number 2, another set of facts that we need to know is that if two lines L1 and L2 are parallel, then their gradient is the same. Again, this is something we've known for quite a while now. And if the two lines are perpendicular, then the product of their gradient is always -1. So if the two lines are parallel like that, then their gradients is the same. And we know that the gradient is from the equation y is mx plus c, where c is the y-intercept. The coefficient of x there refers to the gradient. So if two lines are parallel, then their gradients are the same. So the gradient of the first one, represented by that, must be the same as the gradient of the second one. All right? And if the two lines are perpendicular, if one is perpendicular to the other, then we know that the product of their gradient is always -1. Another way to say this is that the gradient of one of the lines is the negative reciprocal of the gradient of the other. Basically, we just need to move this m2 to the other side. We will find m1 equals negative of 1 over m2. Okay, either way you put it, the same story. If the two lines are perpendicular, then the product of their gradient is always equal to -1, like that. Okay, so we can see that if the gradient of the first one is a half like that, then the gradient of the other one is going to be the reciprocal of this, and then we take the negative of it. So the negative reciprocal of the first one. Okay, if two lines are perpendicular, then their gradient, if when multiplied together, will always give us -1. So that's the second set of information or facts that we need to remember. The third thing we need to remember is that if a line is tangent to another, if a line L is tangent to a curve C. So first of all, what do we mean by it being a tangent to the curve C? It means the straight line L is just touching. So a tangent comes from, I think, Latin word which means to touch. So if line L is tangent, so line L being a straight line, if it is tangent to curve C, it means line L is just touching the curve C like that. So if L is tangent to curve C is the blue one, if L is tangent, then at the point where the two lines touch, they are, if we zoomed in close there, the two lines will be both coincident and parallel. So the two lines are going to be parallel at that point P. They will be parallel and coincident. Coincident means that they occupy the same spot at the same time, like that. So I've just blown up that point there, and if you blow it up, and if that refers to line L, then line C around that point P is also going to occupy the same spot. The key point here is that the two lines are parallel. Other than being coincident, is that they are parallel, and if they are parallel, from the previous statement, their gradients must be the same. All right? And secondly, if line L is normal to the curve, normal means at 90 degrees to. Okay, so if line L, the straight line L, is at 90 degrees to the curve at the point P, all right, then the product of their gradient must be equal to -1, because at that point P, they are at 90 degrees to one another, and so from that previous set of facts, we know that their gradient, the product of their gradients, has to be -1. So these are the important facts we have to remember when we are solving problems related to tangents and normals and with the differentiation. So now let's go ahead and answer our question. The first part of the question asks us to just simply to find the derivative of this, and this we already know how to do from the second lesson, 3.2. So we are given that equation. If we're going to differentiate it, we don't need to make y the subject of the formula, so we will differentiate it implicitly the way it is, okay? And so we start doing this. The derivative of x cubed plus the derivative of y squared must minus the derivative of 3x must be equal to the derivative of 0. The derivative of 0 is of course 0. So the derivative of x cubed is 3x squared. The derivative of y, this is important, the derivative of y squared is going to be 2y, but because we are differentiating it with respect to a different variable, the two variables are not the same, it's unlike this one here. Because of that, we are going to get 2y, but together with the residue dy by dx, and then the derivative of 3x is just going to be 3, and that must be equal to 0 because the derivative of 0 is just 0. If we arrange this formula, if we arrange this expression here, we quickly get that the derivative dy by dx is negative of 3 minus 3x squared, everything divided by 2y. So part A is that straightforward. We have differentiated this relation by method of implicit differentiation or implicit process. Okay, let's go to part 2. Part 2 is going to require those facts that we've discussed. So part 2 says for us to find the coordinates of point P and the coordinates of point Q. Point P was such that the tangent through it was parallel to the x-axis. So we need to remember facts about the situation where the tangent is parallel to the x-axis, all right? So we start. The tangent through P is parallel to the x-axis, and the facts we know about this is if it is parallel to the x-axis, then the gradient of that tangent must be 0. All right, so there is our line L. Okay, at point P, the tangent to point P is parallel to the x-axis, so we know the gradient has to be equal to 0. The gradient of line L has to be equal to 0, but the gradient of line L equals to 0 at that point, because it is a tangent, they are parallel. So the gradient of this curve at that point must also be 0. All right? So the gradient of the curve and the gradient of our straight line must both be equal to 0 because the two are parallel at point P. So we can write that the gradient of the tangent must be 0, and since the two lines are parallel at point P, so is the gradient of our curve. And the gradient of the curve is represented by dy by dx. The gradient of the curve anywhere here can be found by dy by dx. And so we only need to substitute the value of x at the point to determine the gradient at any point, right? So the gradient of our curve is dy by dx, which we found in part A. And the gradient of the straight line there is ml, which is 0. So dy by dx must be 0 at that point. And therefore, we reason, we found the gradient of our curve by that. This is our result from part A. And so this has to be equal to 0. It has to be equal to 0 at that point there. Okay? And so if this equals 0, then it follows the only way that this expression is equal to 0 is that the numerator is 0. So we can directly write that 3 minus 3x squared equals 0. If we rearrange that and solve, we find x squared is 1. And so the possible values of x are -1 and +1. So we are being asked to find the coordinates of point P. We only have possible coordinates, x coordinates. So we still need to find the possible y coordinates. All right. So if we let x be equal to 1, substitute 1 into the function there to get the value of y. If we substitute 1 there, we have 1 plus y squared minus 3. So we get y squared minus 2 equals 0. And so y squared is 2. And so y is positive or negative square root of 2. Which is to say that the potential coordinates of point P there are value of x is 1. The value of x is 1. So 1 comma root 2 and 1 comma negative root 2. Okay, so the coordinates of P from a value of x equals 1 are 1 root 2 and 1 negative root 2. Okay, now we've substituted the value of x equals 1. Now we try to substitute the value of x equal -1 and see if we can get results from this as well. So if we substitute x is -1 there, we will get, if we substitute x is -1 in here, we will get that y squared is -2 because that's going to be -1 and that's going to be +3. So therefore we will end up with +2 here, which we take to the other side to get -2. All right, so y squared becomes -2, but we can't find the square root. We can find the square root of -2, of course, but the result will not be a real number. It will be complex. It will be imaginary. And so we do not have real solutions for y when x is -1. So we do not have any other real coordinate points where the function, where line L is going to be parallel to the x-axis. And therefore, the only possible coordinates of point P for which line L is parallel to the x-axis and tangent to the curve at point P, these are the only possible solutions. Okay, now let's see part B. Part B is to find the possible coordinates of point Q, all right, where Q is a point such that the tangent is parallel to the y-axis. All right, let's see that. So those are our only possible solutions. Let's see that now. So for Q, we are saying that the tangent through Q is parallel to the y-axis. If that is true, we can draw the graph there. So it should look like this. So the tangent, that's the yellow line, is vertical so that it is parallel to the y-axis. If a line is vertical like that, then its gradient is infinite. So our vertical line, which is tangent at point Q, must have a gradient that is infinite. All right, and if that's the case, then we are saying because they are touching, their gradients must be the same. So our line C and line L are parallel at point Q there. And if they are parallel, then their gradients are equal. So we are saying gradient of line L is infinite, and so is our gradient of our line. So the two gradients are equal. Gradient of the straight line must be equal to the gradient of our curve, but the gradient of our curve is the derivative dy by dx at point Q. Our dy by dx is given by that formula, so we are saying that this gradient here must be equal to the gradient of line L, which is infinite, and so this derivative here must be equal to infinity. And the only way that this fraction here is infinite is if the denominator there is 0. So we reason that 2y must be equal to 0. And if 2y is 0, then y is also equal to 0. with the knowledge of value of y, we can now find the possible value of x, values of x by substituting into the equation. If we substitute y is 0 into this equation here, we get x cubed minus 3x equals 0, like that. And if we factorize and solve this, which is straightforward really, we get one possible value of x is 0. The other possible values of x are positive and minus square root of 3, like that. And so immediately we know the coordinates of potential coordinates of point Q is going to be x is 0 and y is 0. That's one possible value. The next possible value is x is positive root 3 and y is 0. And the last one is x is negative root 3 and y is 0, like that. Okay? I went ahead and sketched this function here and then plotted those points to C. So remember, the points P are where the tangent is horizontal. So those must be the maximum and the minimum point. And the points Q are the points where the tangent is vertical, all right, parallel to the y-axis. So I drew that, this function here, and this is how this function looks, or this relation looks when you sketch it. Please try and sketch it and see what I mean. And so my points P and Q, potential values, point P are where the tangent is parallel to the x-axis. You can tell immediately that that's that point here. If we were to draw a tangent there, it will be parallel to the x-axis. The other one is here. So it must be 1 and 1 point something there, and that is actually root 2. Okay, so that's the value we found for P. The other value we found was 1, comma negative root 2. So the other potential value of P is that. And the values of Q must be this point here, okay, where the tangent would be parallel to the y-axis, there, like that. So there are 3 of them here. The first one is this one, which is 0, 0. Then we had root 3, 0. Root 3 is 1.72 something, 1.732. So this is approximately 1.7 there. And the other one is negative root 3, 0. All right? Yes. And so this is the solution to the function. Or usually nobody will ask you to sketch these graphs unless you have the use of a calculator with you. If you don't have a calculator, nobody will require you to actually draw this graph. So I've drawn this just to show you that in fact the solutions we found actually make sense. All right, I hope you've understood this. If you haven't, or if you need any additional support, let me know and I can take you through the process. Okay, if this video, if you find this video helpful, please consider subscribing to the channel and also sharing it with those who might also need it. Thank you. I'll see you in lesson 4, where we will solve another question of this type. Okay, bye.